This is Algebra 2, Lesson 7-3, Logarithmic Functions as Inverse. A logarithmic function is the inverse of an exponential function. A logarithm to base b of a positive number x is defined as follows. This is a little tricky, so try to follow with me. For b being greater than 0 and b not equaling 1, log base b of x equals y if and only if b to the y equals x. You can read log bx as log base b of x. In other words, the logarithm y is the exponent to which b must be raised to get x. For example, since 2 to the 4th equals 16, the logarithm base 2 of 16 is 4. Okay, and that would be written like this. Okay, it would be written log base 2 of 16 equals 4. Because 2 to the 4th power equals 16. Okay. So you can switch between exponential form and logarithmic form and back and forth all the time. Okay. A common log is a logarithm that uses base 10. You can write a common log as log base 10 of x, or you can write it as log of x without showing the 10. Okay. This would be a common log, and this is also the same thing, common log. If you write it, if you put it in the Inspire puts a space here for the base 10. You can either put in the base 10 or you can skip over that. If you skip over that, it's going to assume that it's base 10. A logarithmic scale is when you use the logarithm as a quantity instead of the quantity that they give you. Okay, you use the logarithm of the quantity instead of the actual quantity. So instead of using 54, I use the logarithm of 54. It's kind of a little confusing because you look at it and say you use a quantity instead of the quantity, but it's a logarithm of the quantity instead of the actual quantity. The exponential function y equals b to the x is a one-to-one function. So the inverse x equals b to the y is also a function. To express y as a function of x for the inverse, write y equals log b of x. Okay. All right. So the definition of the logarithm of base b of a positive number x satisfies the following definition: log base b of x equals y if and only if b to the y equals x. Okay. If you can remember x equals b to the y, and you can remember log base b of x equals y, you can transform between the two forms pretty easily. Let's take a look at how we're going to do that. What is the logarithmic form of each equation? So I have 36 equals 6 squared. So in the equation of x equals b to the y, I have x equaling 36, b equaling 6, and y equaling 2. So if I know that, I can put this in logarithmic form because it says log base b, which is 6, to the x, which is 36, equals y, which is 2. So we get y. Log base 6 of 36 equals 2 because 6 squared equals 36. Okay, so this is the logarithmic form of this equation. So now we have 8/27 equals 2/3 to the 3rd power. So my b term here is 2/3. Okay. My y is 3, and my x is 8/27. So if I put that in the right form, log base b, so log to the 2/3, log 2/3 of x, which is 8/27, equals 3. Okay, so in other words, 2/3 to the 3rd power equals 27. Right? Equals 8/27. Okay. All right, 1 equals 3 to the 0 power. So b, okay, happens to be 3, y equals 0, and x equals 1. So log base 3 of 1 equals 0. So in other words, 3 to the 0 power equals 1. Okay. It takes a little remembering how to transfer back and forth from a logarithm to an exponential form and from exponential form to a logarithm. The more you do them, the better you will get at them. Logarithms used to be incredibly important before calculators because before calculators we used this thing called a slide rule. And slide rules would calculate, but only based on logarithms. So people were really, really good with logarithms until the calculator. Once the calculator came into being, people were not as good at logarithms anymore because they didn't have a need to have to know them as well as they used to. So if I'm going to evaluate a logarithm, what is the value of each logarithm? So I need log base 5 of 125, which basically means this: 5 to what power equals 125? Okay. Well, I know that, okay, 5 to the x power equals 5 to the third because 125 is 5 to the third. So x has to equal 3. And that's what we're looking for. We're looking for what is the value of each logarithm. The value of that logarithm is 3, because this would be log 5 of 125 equals 3, because 5 to the third power equals 125. So I have log 4 of 32 means 4 to what power equals 32? Well, 4 to what power equals 32 is the same as 2 to the 5th power. Okay? 2 to the 5th power equals 32, so x equals 5. Okay? Oops, wait. I messed that up. Slow down, because I've got 4 to the x. I don't have the same power. Okay, I don't have the same base. I have 4 to the x instead of 2 to the x because this is a 2 and this is a 4. So I need to think about this. This is 2 to the 2x power, because that becomes 4x. Okay? And that's going to equal 2 to the 5th power, so 2x equals 5, so x actually equals 5 halves. Okay? Then we have log 64, log base 64 equals to the 132nd, which means 64 to the x power equals 132. Well, again, I don't want to take these to this, I need to get them to the same base. I know that 1 over 32 is 2 to the negative 5th power, because 2 to the 5th is 32, so 2 to the negative 5th is 132nd. I also know that 2 to the 6th power equals 64. So I'm going to have 2 to the 6x equals 2 to the negative 5th. So 6x equals negative 5. If I solve this for x, x equals negative 6. Okay. And the more you work with these, the better you are. Now you understand why in chapter 6, I kept harping on being able to change numbers like 64 to an exponential form of some sort, or 132nd being able to change that to an exponential, because I knew you were going to need to use that in this chapter. Now, many measurements of physical phenomena have such a wide range of values that their reported measurements are logarithms, exponents of the values, not the actual value themselves. The Richter scale is a logarithmic scale, believe it or not. The magnitude of an earthquake is the measure of the amount of energy released from its source. Okay? A Richter scale is one of the exponential measures of an earthquake. We always hear, oh, it was a 4.3 on the Richter scale, or a 6.2 on the Richter scale. Okay? So an earthquake of magnitude 5 releases about 30 times as much energy as an earthquake of magnitude 4. Okay? So if you go up, okay, the Richter scale is based on magnitude. So if I have a earthquake at magnitude 3, it's going to be e times 30 to the 3rd power. But if I have an earthquake at magnitude 4, it's e times 30 to the 4th power. So it's 30 times stronger than an earthquake measured at Richter scale of 3. Okay, so let's take a look at this for a second. Okay. In 1995, an earthquake in Mexico registered 8 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook our state, Washington State, in this quality quake. So we want to figure out the formula logarithm of I sub 1 divided by I sub 2 equals m sub 1 minus m sub 2 compares the intensity level of earthquakes, where I is the intensity level determined by a seismograph, and m is the magnitude on a Richter scale. Remember, a seismograph is the little needle that goes across that thing and shows giant peaks and valleys of earthquakes. Compare the amounts of energy released by the two earthquakes. Okay, so the first thing we need to do, we know that it's going to be log I sub 1 divided by I sub 2 equals m sub 1 minus m sub 2. Okay, so I know that means log I sub 1 divided by I sub 2 is going to equal, all I have is the Richter scale, so I got to use the Richter scale. Okay? M is the magnitude on the Richter scale. The first earthquake's magnitude was 8.0. The second earthquake's magnitude was 6.8. Okay, so we have that. So that gives us, log I sub 1 divided by I sub 2 is going to equal 1.2. Because 8 minus 6.8 is 1.2. Okay. Now, if I take a logarithm both sides, remember log is base 10. Okay, we just leave the little 10 off here. If I take a logarithm of both sides, log base 10 of 10 cancels the log out. Okay? So the base 10 of 10 cancels the log out. So if I take a logarithm of both sides, I get I sub 1 divided by I sub 2 equals 10 to the 1.2 power. Because if I take a logarithm, I'm basically multiplying it by 10. So if I multiply this side by 10 and multiply this side by 10, I get rid of the log. This cancels all of that out. And I multiply this to 10 to the 1.2 power. Okay, so I sub 1 divided by I sub 2 is 10 to the 1.2 power, and 10 to the 1.2 power, okay, I sub 1 divided by I sub 2 is going to be 15.8489. Okay? So the earthquake in Mexico was about 15.85 times as intense as the earthquake in Washington. And 15.85 times as intense as just think, if we would have had an earthquake of magnitude 8 instead of the 6.8, the 6.8 did a lot of damage. The 8.0 would have absolutely slaughtered, because it would have been 15 times as powerful, almost 60 times as powerful as the earthquake we actually had. Okay. Graphing a logarithmic function. Okay, these are a bit hairy when you're trying to graph them by yourself. Okay, so what is the graph of log 4 of x? Now, obviously, you could probably graph that on your calculator because it can graph logarithms pretty easily, but I need you to understand how it works and why it works. Okay, so we're going to go through the long and obnoxious process of it because it is important. Okay, so remember, a logarithm is just the same as, you can rewrite a logarithm as an exponential equation. So log 4 of x is the same thing as saying y. The same thing as saying y equals 4 to the x power. Okay. So I'm going to graph y equals 4 to the x power first because if I graph y equals 4 to the x and then because a logarithm, by definition, if you remember, a logarithm was the inverse of an exponential function. So if I know my exponential function is 4 to the x, if I reverse it, I can get my logarithmic equation. Okay? So based on that, I'm going to graph y equals 4 to the x. Okay? So if I graph y equals 4 to the x, if you remember, graphing y equals 4 to the x, if I graph, it's really hard to graph anything. Okay? If x is negative 1, I get 1/4. If x is 0, I get 1. If x is 1, I get 4. If x is 2, I get 4 squared, which is 16. Okay? So here I have that graph right here, y equals 4 to the x. To graph its inverse, I have to graph it along a line that it will reverse over. Now, obviously, that's not going to be the x-axis or the y-axis. It's actually going to be the line of y equals x, because that will produce the inverse. And the line of y equals x is just a line that goes right through the origin diagonally. So if I was to create a line, okay, and we'll draw this. Let's do it red. Okay, this would be my asymptote. Okay, there's my, wow, that did not go straight, did it? I was hoping for a straight line. Still not straight. Why is it not making it straight? One dash, one, two, dash. Okay, so, oh, still not doing it straight. Why isn't it making it straight? Try that one. I really don't want straight one. Well, it's about as big as I'm going to get, because it doesn't like perfectly straight. So, there's my asymptote. Okay, that's part. Okay. Okay, so, actually that's not my asymptote, that's my line of reflection, excuse me. So there's my line of reflection. Okay, so I'm going to choose a few points on y equals 4dx and reverse their coordinates. So instead of having -1, 1/4, I'm now going to have 1/4 -1. Okay, so I'm going to have something that looks like that, and then I'm going to have, instead of 0, 1, I'm going to have 1, 0. Okay, no, that wasn't 1/4, that was dropping the 2's. Okay, so 1, 0 is going to be about here. It's going to be like way over there. Okay, and then instead of having 1, 4, I have 4, 1. 4, 1 is here. And instead of having 2, 16, I'm going to have 16, 2. 4, 8, 16, 2 is going to be right there. So basically, I have a graph that looks like that. And that's terrible long. But, oops, I can't count. That was 16, 4. Okay, let's be able to more carefully in the fence. Alright, so let's graph that again. Oh no! Stop erasing things I don't want to erase. There we go. Alright, so I had the point 1/4 -1. I have 1, 0. So 1, 0 is about here. And I have 4, 1. 4, 2 is here. 4, 1 is there. And then I had 16, 2. 16, 2 is here. I made it go up way too far. So it should be like that. That looks a lot better. Looks more like that one. Okay, so there is my logarithmic graph. Okay. So we now graph y equals log 4 of x. So let's take a look at this because it wanted us to describe the domain, the range, the y-intercept, and the asymptotes. So the domain of y equals log 4 of x will be x is greater than 0. Obviously, I can put in any number for x, and I'm, because if I get -1, it's going to be, okay, technically I shouldn't go below 0 here, because that's actually an asymptote. Okay, so anything greater than 0, so I really shouldn't have changed, I shouldn't have used -1 for it. Okay, and the range, okay, the range will be basically all real numbers. Okay, the y-intercept, okay, it doesn't cross the y-axis. Never crosses the y-axis because the line of reflection is not going to allow it to cross the y-intercept. So the y-intercept is and last but not least, it asks for the asymptote. It has a vertical asymptote. And remember, this graph had a horizontal asymptote of y equals 0. This one has a vertical asymptote of x equals 0. Okay, it has a vertical asymptote of x equals 0, so it's never going to cross x equals 0. It's going to get really close. It's going to get really, really, really close, but it's never going to get to that line. Okay, it's never going to get to the 0 because it can't ever touch that line right there. Okay? So, what does that tell us about logarithms? Other than, yes, they are a bit more incorrect. I agree. So, in summary, the parent function is y equals log base b of x, where b is greater than 0, but it doesn't always equal 1. The same quantities apply to logarithmic graphs as to exponential graphs, as do all the other graphs we've been working with. It's going to be a stretch if the absolute value of a is greater than 1. It's going to be a shrink if the absolute value of a is between 0 and 1. And it's going to reflect if a is less than 0. It's translated by h, horizontally, and vertically by k. And all the transformations together give you this general formula of the equation. Okay. So you can graph y equals log base b of x minus h plus k as the translation h units horizontally and k units vertically of the log base b of x. So the summary of our translations. Okay? If you have log base b of x, your asymptote would be x equals 0. If you have log base b of x minus h plus k, your asymptote is going to be x minus h equals 0, or otherwise known as x equals h. So whatever this is, that's your new asymptote. Okay, your domain for your parent function is greater than 0, and then when you change it, your asymptote is going to change your domain to be x is greater than whatever h is. The range is all real numbers for both equations. So if we have, let's translate an equation for y equals log base b of x. Let's graph y equals log base 6 of x minus 2 plus 3. So we're going to make a parent function for log base 6 of x. Okay, just to remind you of this, because I have this little table here, and you might be wondering how in the world they got the y values for these. Okay, so I have log base 6 of 6 equals, okay, so 6 to the x power equals 6. Well, x has to equal 1. That's how we got the 1 right there. So log, okay. So the second one over here, you have log base 6, where x is 1. So you're going to have 6 to the x power equals 1, so x has to equal 0, and so on and so forth. So that's how you get these numbers right here. So we graph these numbers. Those numbers happen to be the graph in red. Okay, so we graph the graph in red, and the asymptote would have been x equals 0, right? Because if you look at it, the asymptote here for a logarithm is x is equal to 0. So it can't cross the y-axis, in other words. Okay, so here's your x equals 0 line right here. It's the y-axis. So there's my logarithmic graph for log base 6 of x. But now we want log base 6 of x minus 2 plus 3. So this is going to shift it left 2. This is going to shift it up 3. So I just take these points, like for this point, to be right 2, not left 2. I always do that. Y. Right 2. And up 3. So now I'm going to take my points, and if I look at this point right here, and I shift it right 2 and up 3, it ends up over here. Okay? This point here goes right 2 and up 3. It goes here, and so on and so forth. Then I draw my new graph, and here's my new asymptote. X is equal to 2, because it ends up being h. Okay, so there's my new asymptote. So that's how you graph a logarithmic function. Most of the time, I will keep you with basic parent logarithmic functions. Okay, and I'm not going to ask you to graph a ridiculous amount of them, but I will ask you to graph them. You can check them with your graphing calculator, but you need to graph them without the graphing calculator, because on the quiz, I will ask you to graph them without the graphing calculator. Okay, so this is basically the introduction of logarithms.